I guess the memories maybe are not completely there. So let me recap a little bit what we did last time. So we were in the course of proving that rescaled quadrangulations, uniform quadrangulations on the sphere, converge to some limiting object. And in order to do that, we used the fact that we have a concrete way to view a pointed uniform quadrangulation. So this is a uniform quadrangulation with n faces and rooted. And this is a uniform vertex of Qn. So we have a concrete way of viewing this quadrangulation as the image by the Corey-Vauquelin-Schaeffer bijection of a uniform label tree that we denoted by T and Ln. Okay, so this is a uniform element of T, N, which is the set of label tree with n edges. Okay, and since we discussed at length, the convergence of this object, well, the hope is that we can deduce that this converges to some limiting object as well. Okay, so how did we do that? We actually encoded the distances within the map by using a function, a 2-parameter function defined on 0, 1. So the definition was as follows. So defined dn of j of I over 2n to j over 2n as the distance in the quadrangulation between vi and vj. Okay, so this is the graph distance. And this, as usual, is the ith visited vertex of Tn in contour order. Okay, and as we saw, the set of vertices of Tn is really the same as the set of vertices of Qn, except the the root vertex or the distinguished vertex V star. Okay. And then we had this renormalization factor that arises in the scaling limit of the labels defined on the tree, which is 8n over 9 to the minus 1/4 there. Okay, so this object was really the rescaled, if you like, distance function. And since I and j are between 0 and 2n, I over 2n and j over 2n are elements of the interval 0, 1. Okay, so this is an object defined on the interval 0, 1 times the interval 0, 1, and it's of order 1 because of this renormalization that we have here. Okay. Okay, so we extend to a continuous function on 0, 1 squared. So from 0, 1 squared to r plus, so this is just defined on a grid, if you like, the set of points of the form I over 2n, and we can extend it to a continuous function. It's not really, it doesn't really matter how you do it, as soon as it's reasonable. Okay, and then we stated the following. So we almost fully proved the following result. So I was a little bit sketchy, if you remember. So from every subsequence, one can extract a further subsequence along which so dn as a function converges in distribution to a limiting d. Okay, so that's in C01 squared. And in fact, I stated it in a slightly different form. I said that if you consider not only this process of distances, of rescale distances, but also add in, the contour, the rescale contour function of the tree, and the label contour function of the tree, then this whole triple converges to the limit E, Z, D. Okay, so again, this is the contour and label processes of T and Ln. And in fact, okay, so, and this is in distribution, this time in C01 squared times C of 01 squared, okay? The first two components are functions of 01, okay? On 01. And as we saw, in fact, it's really sufficient to prove that the set of laws, the family of laws of these processes here is tight, okay? Because once you know that this is tight, then you just have a product space here, okay? We already know that these converge, okay? So the whole family here of the law of this triple, if you like, is really tight as well, okay? So you can also choose subsequences. So the reason why we want to keep this contour and label process is that so far we don't know what the law of this capital D is, and what we hope to be able to do is to define D as a function of what we know, okay? Which is the encoding functions E and Z of the Brownian tree with Brownian labels, okay? Another way to say it, okay, so far, the exact distribution of D is not known, okay? And somehow we would like to be able to write D as a function, let's say, so this is really in quotes, as a function of Ez, where this function is really a continuous analog of the Curie-Vauquelin-Schaeffer bijection, so in the same way, as the fact that Qn, is, or maybe Qn V star, doesn't really matter here. Qn V star is the image of the label tree by the Curie-Vauquelin-Schaeffer function. Okay, and this somehow should be a continuous analog of CVS. Okay, and that's the reason for taking all these processes along in the statement of this theorem. Okay, so before commenting further on that, let me, this statement is really a convergence in distribution of, random functions, random distance functions. So maybe I should add also that D, we mentioned that last time, is a pseudo distance function on 01. Of course, it's random, and it's a pseudo distance on 01. So the first thing we would like to say is that this actually implies a convergence of maps in the Gromov-Hausdorff sense. Okay, and this is indeed true and very reminiscent of what we did earlier in this set of lectures for trees. And this says that along such converging subsequences, it holds that so the set of vertices of Qn rescaled appropriately with the graph distance, rescaled appropriately, converges in distribution as n goes to infinity to a limiting metric space. And this metric space is none other than, we already know that the distances should be given by D, okay? But again, D is only a pseudo distance, which means that some points of 0, 1 can be at 0 distance for d. Okay? So we want to identify these points using the equivalence relation. When you have a pseudo distance, then the set of points that are at 0 pseudo distance forms an equivalence relation. So we can take a quotient set here, and endow this quotient set with the image of the metric under the canonical projection. Okay, it's really a shortcut, a notational shortcut here, but there is really nothing mysterious to this. Okay. So it holds that this convergence holds in distribution for the Gromov-Hausdorff topology. Okay. And this limiting object here, you would like to be able to call that the Brownian map in the same way as Brownian motion is the limit of uniform random walks, and that's actually the reason why people want to call the scaling limits of random maps Brownian map. The only thing is that we don't know yet that the limit has a unique law. Maybe at this time the limit can depend on the choice of the subsequence that we made here. Okay, okay, so the proof of this is in fact very easy. So I'll go fairly quickly over it. So let us assume that dn converges to d in the almost sure sense rather than just in distribution. Okay, again using the score code representation theorem. Okay, so it's always possible to assume that the underlying probability space is such that this holds, and of course it's uniform. Then goes to infinity again along a subsequence, as in the statement. And then let us construct a correspondence between these two spaces. Okay. So how do we do that? Well, there is a very natural way to do it, which is simply to consider the set of pairs of the form vi. So actually, let us call that straight away v2 and t to p of t in 0, 1, where p is the canonical projection from 0, 1 to S. Okay, S is the quotient set here, so is the canonical projection. Okay, so the canonical projection allows me to see, if you like, every point of S as being coded by a number between 0 and 1. Okay, and I want to associate with this number or this point the vertex of Tn visited at time 2 and t. Okay. And if you like, this vertex is also a vertex of Qn. So clearly, Rn is a correspondence between V of Tn and S. And V of Tn, again, I want to view that as V of Qn except the vertex V star. So in order to show Gromov-Hausdorff convergence, we should have a correspondence between the full set VQn, but this is really irrelevant here. Okay, but so this will be sufficient given the obvious fact that the Gromov-Hausdorff convergence between the set VQn as the graph distance to the subset VQN minus V star with the graph distance is at most 1. Okay. Why is that true? Well, that it's clear. Okay, it's clear that V star is in any case at distance at most, at distance 1 from one of the vertices of V of Qn. Okay, so if you take, the correspondence between V and Qn and itself, so if you take a correspondence that assigns with every vertex here its analog here, itself, and with V star you assign any of its neighbors, it's clear that the distortion of that will be at most 2. Okay, so that's really an easy exercise. Okay, so consider R to be the set VV for V different from V star, union, let's say V star U, where U is some neighbor of V star. Okay? So therefore, if you rescale all the distances, okay, so if you apply the scaling factor here, then this will become negligible in the limit. Okay? It's clear that multiplying Gromov-Hausdorff distances amounts to multiplying the distances that you want to compare. Okay? Okay, so again, the fact that you have just a correspondence between these sets is irrelevant in the limit. And now we have that the distortion of Rn, so let's recall what it is. It's the supremum over all pairs of points that are in correspondence. So here points in correspondence are just parametrized by a single time t. Okay, so it's really the sup over t prime in 0, 1 of so dqn of v to nt v to nt prime minus d of tt prime. Okay, is that clear? So I should really have p of t and p of t prime, but by definition, this quantity does not depend, in fact, on the choice of t and t prime within their equivalence class for the equivalence relation here. Okay, and this is nothing but dn of 2nt divided by 2n, 2nt prime divided by 2n, and by uniform convergence of dn to d, this goes to 0. Okay. So this is really almost verbatim the proof that we had for trees. Once you know the convergence of the contour function, or we knew how to deduce from that the convergence of the distance functions, and then we get convergence in the Gromov-Hausdorff topology. Okay, so the goal now is to identify the limit d. Okay, so we really want to see it as a function of the tree, the Brownian tree. So in fact, there are a couple of very elementary properties that we can deduce straight away from what we have so far. So elementary properties. So first of all, so let maybe S star be okay. In fact, it turns out to be almost surely unique time in 0, 1, at which Z achieves its minimum. Okay, so z of s star is equal to the mean of z over 0, 1, which I already denoted, I think, by z bar. Okay, so the fact that it's almost surely unique is not at all straightforward. You need an argument to do that, but I won't do it here. And in fact, it's not strictly needed for what I'm going to say, but it's always convenient, I mean, to know that it's unique and that there is no ambiguity in this terminology. So proposition. So almost surely, it holds that the distance from every s to s star is given by the difference between the labels zs and zs star, which is the minimum label. And that's almost surely for every s in 0, 1 simultaneously. Okay, that's maybe the property 1. Property 2 is that, so for every st in 0, 1, let us suppose that s and t actually encode the same point in the Brownian tree. Okay, that is the dE distance between d and s and t is 0. Then the claim is that this implies that the distance for d is equal to 0 as well. Okay, so points identified in the Brownian tree are also identified in D. The third property is that for every st in 0, 1, we have an upper bound, which is given by the following function. So let me call that dz of st. And this dz of st is defined in exactly the same way as the distance for dE. Okay, so it's z of s plus z of t minus twice. So here there is actually just a little twist here. So I want to call that maybe z with a little arrow from s to t. Take the supremum with z arrow from t to s. So here I need to explain why I didn't just let it to be z chech st, you know, the minimum of z between s and t, as we did for the Brownian excursion. And the difference here is that what I want to see, I want to look at the interval 0, 1 really as being a circle in which 1 has been identified to 0. And I want to consider, you know, 2 points s and t on this circle as encoding 2 arcs. Okay, there is really the arc that goes from s to t and the arc that goes from t to s. Okay? Now what I want to do is to define z bar of st to be the mean of z on the arc, so on the clockwise arc. Okay, so clockwise here doesn't really make sense, right? It's really because of this convention here, but it's really the arc that goes from 0 to 1 and then back at 0. Okay, clockwise arc from s to t. Okay, and so therefore I take the minimum of z on this arc from s to t and the minimum of z on the arc from t to s, and I take the maximum of these two quantities. So why do I have to do that? Well, the main difference between z and e is that, if you remember, e is a non-negative function. Okay, so that was e, whereas z, obviously, which is Brownian motion on the continuum tree, is a function that you know, takes both positive and negative values. Okay, so therefore, if you take 2 times maybe s and t there, okay, so maybe let me put it in another way. If you want to assign a tree, to associate a tree with the process z, maybe what you should first do is to reroute this process z at the minimum and do what I already called last time in a previous lecture a Vervat transform. That is, you want to take this part and to put it on the other way, on the other side. Okay. And then in this case, you really don't want to take the minimum between S and T here, but really the minimum between the image of S on this other side here. Okay, and consider really the tree coded by the positive function associated with Z. Okay. And if you think about it for a little while, you will see that this does exactly the job. And for instance, if you if you replace Z by E, then this formula is also totally valid, except that, you know, one of the intervals from S to T or from T to S actually passes through 0, which means that the minimum of the excursion is 0, okay, because the excursion has only non-negative values. And in that case, this interval will not count. It will always be smaller than the other one. Okay, so I'm sorry for this rather you know, technical point, but the thing is that if you want to assign an R tree, a real tree, with a function which is not positive, okay, which is not an excursion, if you like, this is really the definition you should adopt. Okay, and then last point is that for every S and T, we also have a lower bound, and this lower bound is simply given by the absolute value of the difference. Okay, very simple lower bound. Okay, so of course, so we'll prove this. It's rather easy, but of course we are yet far from proving. I mean, from identifying D. Okay, because certainly you can find situations where these two bounds do not match. It's very simple to see. And in fact, you can find, you know, let's say we'll see in a second. This upper bound somehow is rather good, but this lower bound is really poor. There are ways to make this lower bound much better. Okay, so the proof essentially just follows by limiting arguments. So one follows from the fact that, so recall that the distance in Qn from V to V star is just equal to the label of V minus the minimum of the labels plus 1. Okay? And, you know, we're almost there. Just replace V maybe by V2 and T, you know, the vertex visited at time 2 and T. Okay. In this case, this is just ln of 2nt divided by 2n minus, you know, with obvious notation, the mean of ln plus 1. And after renormalization, by 8n over 9 to the 1/4, this converges, well, both to the distance between T and T star, and Z at time T minus the minimum of Z, which is the limit of ln. Okay, and the plus 1, of course, disappears because you multiply it by something that goes to 0. So what is, sorry, that's S star. So in fact, what is not completely clear here is that you do have convergence. Okay, this part is clear. You know, this V2 and T will converge somehow to the point coded by T. It's not entirely clear, though, that V star does correspond to the point S star. So here we use the fact let's say that if In is a time you know, a neighbor of V star is visited. Okay, so it's a rather long way to say that V of In is adjacent to V star. Then necessarily In over 2n has to converge to S star as n goes to infinity. Okay. And why is that the case? So indeed, at time In, the label process, you know, reaches almost its minimum, just the minimum shifted by 1 because it's at distance 1 from V star, which achieves the global minimum. Okay. So you see, if you know In over 2n is a quantity in 0, 1, so up to extraction it converges to some limit, and this limit has no choice but to be a point at which the limit of this, the value of z at this limit point, is equal to the smallest value of z. Okay, so this implies that z of, let's say, S bar is equal to z bar for every subsequential limit of In over 2n. And therefore, by uniqueness, S bar is equal to S star. Okay? And then what you do is you just say, you use the triangle inequality and say that this distance is at most 1 away from the distance from V to NT to VIN, because VIN is a neighbor of V star. Okay, so it's again a rather tedious you know, discussion that comes from the fact that V star, unfortunately, is not coded within the tree. Okay, but it's very close from there. So note that we used here, in fact, in a crucial way, the fact that this S star is unique. But in fact, otherwise, if we don't know that, it's not so bad. It just means that S bar will be a point at which you achieve the minimum, and the result is the same. Okay, so now let's look at 2. So 2 means that if S and T code the same point of the CRT, the continuum random tree, then they're at d distance 0. So this comes from the fact, also from a limiting argument, that if dE of ST is equal to 0, then I claim that there exist sequences In and Jn such that In over 2n converges to S, Jn over 2n converges to T, and V of In is equal to V of Jn. Okay? So, yeah, maybe I should have made this comment here, but actually it should come at that point. So from now on, always fix a subsequence as in the theorem, and assume that the triple Cn, Ln, Dn converges to E, Z, D, not only in distribution but in the almost sure sense. Okay, and we know that we can do that. We fix the subsequence, and of course it's along this subsequence. Okay, so every time now that I let n go to infinity, I'm really considering n going to infinity along this particular subsequence chosen for me by the theorem, or a further subsequence of this subsequence. Okay, and here you see I already used this kind of almost sure properties, for instance, in this argument. Okay, so back to this discussion. So why is this property true? It's rather easy to see, because you see if S and T code the same point on the Brownian tree, it means that they are facing each other under the graph of the Brownian excursion. Okay, but then we know that Cn, you know, the set of contour processes, converges uniformly. So it's not very hard to convince yourself that it's possible, you know, to find these two sequences In and Jn that also face each other under the graph of the function Cn and converge after renormalization to S and T. Okay, if you want, they're really counterparts. So there is a little argument to think about here, and the important thing here is that the Brownian excursion does not assume, you know, does not reach its local minima more than let's say 3 times. You know, it's Brownian excursion does. This is somehow the worst situation that can that could occur. You know, and the problem is that if you pick, for instance, S and T like that, you see that it's very well possible that. Wait a second. No, sorry, you don't even need that. It's just the fact that you have to choose the In and Jn a little bit carefully. Okay, if for instance you have S and T that are located like that, it's possible that if you choose In there, it's possible that the tree, the process Cn, is always above this level. Okay, so you have to be just a little careful and choose In, which is a bit up there. Okay, so sorry for the confusion, but it's you know, this is really an exercise. Okay, and once you have this, then the proof is immediate. Okay, then because they code the same point in the tree Tn, well, it means that they are the same point in the map. Okay, so dqn of Vin Vjn is equal to 0. Okay, because they are equal. And then after rescaling, get d of st equal to 0. And now 3 and 4, so it'll be maybe a little go a little faster on these points. So 3 comes from the upper bound from the analog statement in the discrete case that we saw last time. And let me just recall very quickly how we obtained that. So looking at the tree Tn, okay, we wanted to construct a path going from Vi to Vj. And we did that by considering, you know, the chain of the geodesic of successor to V star until they meet at a certain point. Okay, and the upper bound that we obtained was of the form dqn of Vi Vj is less than ln of I plus ln of j minus twice the minimum of ln between I and j plus 2. Okay, where again the minimum of ln between I and j is what you get by going from I to j on this side somehow. But you get also the same upper bound by going rather from j to I, so on the other side here, okay, and you get the result by taking the best of the two bounds. Okay, and then you pass to the limit. So do the same with I and j exchanged, and then pass to the limit. And 4 is very similar, so it's just a consequence of the fact that the distance from Vi to Vj, well, is at least the difference of the labels. And this, we commented on that. It's a very simple property of the Schaeffer bijection. In order to go from a vertex to another, you have to cross an edge along which the label increases or decreases by 1. Okay, so therefore, if you want to go from any vertex to any other, you have to do at least this number of steps. Okay. So here, at that moment, we're in fact not that far from understanding that this metric, this limiting metric space, SD, is indeed a kind of image of the Brownian tree by some continuous analog of the Corey-Vauquelin-Schaeffer bijection. And why is that? Well, so we started from the interval 0, 1, and now we have really one first identification, which is given by this function dE. Okay, if we identify points in 0, 1 by identifications of the Brownian tree, then they are the same point of the map. So, if you like, we have this first quotient by dE equals 0, and that gives the Brownian tree. And this somehow is, if you like, a subset of points in my limiting space S. But then, so this upper bound tells you that if S and T also encode the same point now in the tree coded by Z, then they're also the same point in the map. Okay, if dz of st is equal to 0, then d of st is equal to 0. So, in a sense, this statement 3 is really stronger than this one, but with this different notion of distance. Okay, so we really have a second quotient, which I'm going to show actually on the same picture, which tells you that. So, what does it mean that ds of st is equal to 0? So that really means that if S maybe codes this point here, so this is really the point PE of S and PE of T, saying that dz of st is equal to 0 means that when you travel from S to T, either on this side or on the other side, so maybe I'll use two different colors. Okay, when you travel from S to T on either of these two sides of the tree, then it must be the case that all the labels that you encounter are bigger than the label, bigger or equal to than the label of S. Okay, and in particular, the label of S has to be the same as the label of T. Okay, so this is equivalent to the fact that Z of S is equal to Z of T, and Z of U is always bigger than this common value for all U in either the cyclic interval from S to T or the cyclic interval from T to S. Okay, which are denoted by these two colors on the blackboard. Now, let's imagine, for instance, that this property here holds on the red interval. Okay, so this really means again that the label of this guy and the label of this guy are the same, and in between all the labels are bigger. Okay, so Z of C, let's say, is bigger than Z of A equals Z of B, where A is this point and B is that point. But that's really an analog of the Schaeffer construction. Okay, remember that in the Schaeffer bijection, the Corey-Vauquelin-Schaeffer bijection, we had to link by an arc a vertex with the next available vertex of strictly smaller label. Okay, in the continuum, this distinction of next vertex of strictly smaller label disappears because you know, the difference between the two labels has to be 1, and after rescaling, this 1 disappears. So it really means here that you have an identification between points of same label that are separated only by points of bigger labels. Okay, and of course now you can have many of such points. Okay, so maybe these two also satisfy this property. Maybe these two satisfy it, and so on and so forth. And maybe these two ones as well. Okay. Okay, so this second quotient is, you know, analog to the Corey-Vauquelin-Schaeffer construction. Go to the same label, go to the next available vertex with the same label as you, okay, and link it by an edge of a vanishing distance. Okay, so far this is still a bit vague somehow what we are doing here. So what can we, what kind of concrete statement can we obtain from this consideration? Well, one very concrete statement that we can get is that, if you remember, one of the nice aspects of the Corey-Vauquelin-Schaeffer bijection is that it allows you to construct geodesics. You know, it's better than just giving the distances to V star. Somehow you can construct the whole geodesic by taking successors. And in fact, this is also possible in the continuum. So let's say proposition. So let T be in 0, 1, and for every R between 0 and the distance between S star and T, we let so gamma d T of R to be the first available S bigger than T such that the label of S is equal to the label of T minus R. And this I want really to call that, the rth successor of T. Okay? In the Corey-Vauquelin-Schaeffer bijection, you had to look for the first available vertex with label less than the one you started from. And here I do exactly the same. Okay, I want to find the first available vertex, or the first available point bigger than T, at which the label achieves this value. Okay? And of course, I should do that not only on the interval 0, 1, but really on the cyclic interval associated with the interval 0, 1. Okay, so this is really the first on the arc from S to T in, let's say, 0, 1 with 0 identified with 1. Okay, so if you can do this picture, S is there maybe and T is there, and you have to take this cyclic interval. Sorry, that's exactly the opposite. T is there, and then you take the first S after T so that you achieve this value. And similarly, I want to call gamma T G of R to be the supremum S less than T in this cyclic order at which we achieve this value. And then the claim is that these two times, these two random times, they encode, in fact, the same point in S. Okay, so I want to denote that by gamma t of R for every R as above, and gamma t, now defined as a mapping from 0 t of S star t to S, is a geodesic from, you know, the point which achieves the minimum label, which I really want to consider as the analog of V star. Well, it's actually the opposite. It's going to, okay, and from x equals p of t. Okay, and the proof is really not very hard. Actually, it's a good exercise. So let me draw a picture of the process Z, and let's imagine for a second that Z is really rerouted at the minimum. Okay, so I really want to consider Z after the time S star where it achieves its minimum, and then I have this time t. Okay. So by definition, if I fix the value of R here, then gamma d t of R is the first time after t where I achieve this value. Okay. And similarly, gamma g t of R is the last time before t where I achieve this same value. Okay. So now what you can see immediately is that these 2 points, they just face each other under the graph of the function z. Okay. So therefore, the distance between gamma g of R and gamma d of R for this Z process is equal to 0. Okay. So the same must be true for D by this property here. So that's, you know, the first remark. And now the second remark is, now let's take another R prime maybe. Okay. So this time I have to go down to the first time where I achieve this value R prime. So this is gamma t d of R prime. Then note that, well, Z of t, sorry, Z of S is always greater than or equal to, by definition, gamma t d of R prime on the interval from gamma t d of R to gamma t d of R prime whenever, let's say, R and R prime are fixed with R less than R prime. Okay, it's just the fact that you know, this is the first time I achieve this value, so before I have to be bigger than that. And then this implies clearly, well, let you see the details for that, that gamma t d of R, gamma t d of R prime, well, is in fact equal to this distance here. Okay, this is really R prime minus R. So in this case, upper and lower bound for D, given by 3 and 4 in the previous statement, they match in this case. Okay, because the value achieved at that time is really, so it's really z of this time minus r, but then you take differences, okay, and sorry, z of this time minus z of t, and at this time you achieve the value z of t minus r, so the z of t disappear. Okay, so and they match in this case, so they actually give the exact value of d, let's say of gamma tr to gamma t r prime, and this value is given by the Euclidean distance between r and r prime. Okay, so that exactly tells you that gamma t realizes an isometric embedding of this interval into S. Is that okay? So okay, let me maybe take a couple of minutes to conclude. Right. Okay, so I want to conclude with two remarks. The first remark is that we've been insisting a lot on the Brownian tree in the first lectures on scaling limits of random trees, but now it's clear that we have a second tree in the landscape, and this tree is given by is coded by the function z. And this statement tells you exactly what this tree looks like. Okay, this tree. So the tree coded by z let's call it maybe tz, which is the quotient of 0, 1 by points identified by the dz distance here, should be seen as a tree of geodesics to V star, or actually to X star. Okay? So what does it mean? It means that, well, from X star we have, identified a family of geodesics that all go to X star, from any point in the map. But if you think about it, this definition of the geodesic is actually the exact definition of the geodesic in the tree coded by Z, pushed forward inside the map, okay, by the canonical projection. So somehow you have this tree coded by Z, which I really want to think about straight segments all going to X star, except that when you push this tree in the map, some of the points can actually get identified. Okay, so maybe two geodesics might arrive at the same point in the map. There can be also identifications. So this picture is exactly dual, if you like, to this picture. You can see either the limit as the CRT with certain identifications, or as the tree coded by Z with some other identifications. And in some sense, this picture is a little more faithful to the metric structure of the underlying space, because the red paths that you have here are really pushed into geodesics in the space SD. Okay, so it's should really think about this as a tree with some let's say pairs of geodesics that meet at certain points. Now this picture, in fact, we have seen it before in the discrete case. If you remember, when we constructed the inverse map of the Corey-Vauquelin-Schaeffer bijection, we used what I call the flow of cars coming from X star that I associated with Detroit, the city from where all the cars come. And then this flow of cars invades America by going along the ring roads around each cities. you know. And this is exactly what you see here. You know, the fact that the flow of cars were going along the ring roads and satisfied the priority conditions so that this flow of cars did not reflect on itself, if you like, or did not cross itself, was exactly constructing a tree in the map. And this tree is nothing but that tree which is here. Okay, so it's analog to the flow of cars in the Boutier di Francesco Guiter construction that I gave earlier. Okay. So that's the first remark. It tells you what the tree TZ does, and the second remark, on which I want to finish, is that, well, so far we are not really we haven't really identified the Brownian map. Okay, so the problem is that we do not yet know a formula, an explicit formula for D, which is in strong contrast with the situation for the CRT, because for the CRT we had the Brownian excursion, and from that we had a completely explicit formula for the distances in the tree. Okay, so actually let me just explain to you what this formula should be. Well, we don't have a formula, but we have an upper bound here. And certainly this upper bound, there is no reason why it should be optimal. There is no reason why going from any point to any other point you should go in that way. Otherwise, the Brownian map would be a tree, if you like. Okay, and clearly it's not the case. Okay, so what should we do? Well, we should say, well, in fact, going from that point to that other point, maybe in fact we want to take a shortcut somewhere. So maybe we want to go down there, then up there, take a shortcut, and then do that. Okay. And maybe if we do that in the optimal way, we can find the true distance. So how do we do that? Well, note that if I'm given STU, let's say STUV in 0, 1, with the distance between U and V in the tree equal to 0. So they equal the same point in the continuum random tree. Then certainly D of ST is less than D of SU plus D of UV plus D of VT. But this is equal to 0, okay, by the property 2. Okay. And then this is less than dz of SU plus dz of VT, okay, by the upper bound 3. And more generally, it holds that D of ST, you know, by taking more intermediate points like this, certainly has to be less than the quantity which I want to call D star of ST, and which is the infimum of all sums of the form dz of SI Ti, such that I ranges from 1 to k, S1 is equal to S, Tk is equal to T, and Ti is at 0 distance from Si plus 1 for 1 less than I less k minus 1. If you want, it's a shortcut. Okay, it's the exact same argument as what I did before. Okay. And now the thing is, so why did I actually use the upper bound? It's just because I know these quantities. Okay, so this is really a function or measurable function of E and Z. Okay, and the claim, the theorem, is that in fact this upper bound is really inequality. Okay, so it holds that D is equal to D star almost surely. So it's actually a good exercise to see that this star, it has to be a pseudo distance. Okay. In fact, it's, if you like, it's the largest pseudo distance that satisfies these two properties, this upper bound here and this identification there. Okay. So this statement somehow tells you that the other bound is true, and so this theorem is really due to Le Gall and myself using two different approaches. And this theorem really identifies the limiting space. Okay, so so sorry for going over time. So what I want to do in the remaining 2 lectures, I want to spend again 30 minutes to give some of the important properties of this limiting space. What are its topological and metric properties. And after that, I want to attack a completely different topic, which is that of local limits of maps. Okay. And that's all for today. Thank you. Any quick question before lunch? It's lunch then.